Hello, this is the first video in a series where we're going to discuss how does the bracket notation for laying out mathematical proofs work. The purpose of the bracket notation is primarily pedagogical because it helps one understand the structure of mathematical proof when one is first exposed to the whole realm of mathematics dealing with proofs, and of course that's the first door wants to open when one enters into abstract mathematics. Okay, so just let us begin with a general overview of how the bracket notation works before we go in later videos into specifics of how does it work in each particular type of situation. The general idea is to structure your proof as a sequence of mathematical statements, but as such one encounters, so let's draw these lines representing some mathematical statements. So for example, if you read a proof of some theorem from a certain theorem, from a certain book, you will see that the proof consists of a series of sentences. And these lines more or less correspond to those sentences, although very often in written mathematical proofs there are steps that are skipped, which the reader is supposed to recover on her or his own. In the bracket notation, we have flexibility of also skipping the steps. However, we can also insert the missed steps without having to change the structure of the original proof too much. Okay, so when we have a mathematical proof that consists of a sequence of statements, the idea is that the standard thing is for us to begin with nothing, with an empty statement, and then eventually to arrive to a conclusion, which is the theorem we wanted to prove. So this orange line is going to represent the theorem that we wanted to prove. Now, in this blank first line, you don't have anything there, but you actually might have lots of things in there without them being written out, because typically theorems rely on axioms. And the axioms are not necessarily specified either in the formulation of the theorem or inside the proof. The axioms is something that is given to us separately, and then when we approach a theorem, the understanding is that those axioms that were given to us, we can use all of them. And so in principle, these axioms could have been taking the place of this empty line there, but that's not how it works. So we do not want to start with anything, but we do understand that when we say we don't want to start with anything, we mean we don't want to start anything on top of the axioms that are already given. Okay. So then in the actual final proof, the empty line would not even be visible. And then, of course, the philosophy of this is that you want to start with no assumptions and eventually get to your theorem in a sequence of logical steps. So the idea here is that every next line can be deduced from the previous lines by means of some fixed logical rules. And there goes another thing that we don't specify within the proof, and namely that's the underlying logical rules by which the conclusions are made in a proof. So every next line, let me repeat that a bit more clearly. Let's say we take this line. So once the composition of a proof of like this should be sequential. So, well, maybe the composition is not necessarily sequential, but when we read the proof, this process should be sequential. So we have these few lines, and now we are at this point in reading the proof. We've read all the previous lines, and now we want to read the next one. And as we read the next one, we want to confirm that the next one is a valid conclusion from the previous ones. So this line that I've highlighted here should be a logical conclusion of all of these previous lines. Okay? And the rules of logic, according to which that's the case, also like axioms, they have to be specified separately. And usually rules of logic change very little. They almost never change. The axioms change a lot because depending on which mathematical theory you're working in, that will determine what your axioms are. But the rules of logic are more universal. They span across different theories. Although one can also change slightly the rules of logic. One of the standard things one can do there is to drop one of the rules of logic, and then you want to see how much you can establish with fewer rules than what you had initially. Okay. Now, this thing that I said that every next line should be a conclusion of all the previous lines, it is actually not quite true. There is one exception when this does not have to be like that. And when that happens, that line is called an assumption. So the way assumptions are indicated in a proof is by putting the line that's an assumption slightly more inside than the other lines appear. So now what I'm going to do, I'm going to treat this third line as an assumption. So this will be our assumption, and the way I can see that it's an assumption is that there has been this space created here. The role of the assumption is to say that we're no longer claiming in the assumption that this thing is true. Instead, what we're doing here, we're considering the possibility of this being true and seeing what conclusions can be drawn if this thing were true, right? So that's the role of assumption, to say, okay, imagine this were true, then what could we establish with that assumption? And the lines that appear below the assumption, which are aligned at the same spot where the assumption was, which is different from the spot where all the others are aligned. So these lines are conclusions which are dependent on this assumption. So when I said before that one of the lines, for instance this one, should be a conclusion of all the lines before, this rule still applies here. So this line here must be a conclusion of all of these lines, including the assumption that once we pass through this stage, we can forget whether this thing was an assumption or not. It doesn't play any relevance anymore for this specific line, as long as it's in the same alignment. And the same is true, of course, for this line. So this line should be a conclusion of all the previous lines, just like any other line should be. So the only time when a line does not have to be a conclusion of the previous lines is when the assumption is introduced. So this line shouldn't be a conclusion of anything. It could still be a conclusion, but that plays no role. We don't have to check that anymore. So literally, we can write here anything we like. In a way, this is our creative spot in a proof. And then there could be quite a complex structure of assumptions and conclusions in the proof. For example, there could have been actually this structure where already the second line is an assumption. Now, what happens under the assumption, we've already discussed, the lines appearing under are conclusions, unless there is another space created, in which case there is a second assumption and the rest of the lines are conclusions. But then, when we go back to the original alignment of the lines, right? Like, for example, here, when we go back from here to there, when we make that step, you see this line is no longer aligned according to how that assumption was. And so this means that we are stepping out of the assumption. It means that in this line specifically, that line, that assumption no longer applies. And that does mean that everything that we've been concluding here, because all of these things relied on this assumption, right? All of these things, they can't be used anymore in this line. I mean, they can be used as logical steps in the sense that, for example, this line cannot be a conclusion of that line, because that line relied on actually two assumptions, this one and this one. And for this line, those assumptions have been dropped. So they're not assumptions anymore. At this point, we no longer are assuming that the second and the third line are true. We have no such assumption anymore, and so we can't make use of those facts that relied on second and the third line being true. So that's how you can think of it in terms of truth of statements. Then you might be wondering, okay, if that's the case, if this line cannot make use of the conclusions made within the assumptions, then how do we I mean, what's the whole point of having made these assumptions if we can't use them, right? Now, the interesting thing, and that's what we will address in subsequent videos, is that even though you can't, for this line, even though you can't treat the previous lines that appeared within certain assumptions out of which we stepped out now, you can't treat them individually, these lines, you can still make a conclusion out of the entire process of having performed this argument. And we will discuss this in more detail, but just to give you one simple example, if this line says alpha, so let's say alpha is some mathematical statement that has been assumed here, and by these steps we've concluded eventually beta out of it, then although in this line neither alpha nor beta are true anymore, in this line we can still write alpha implies beta. And that's to say that, of course, this single statement represents the dynamics of what happened here from second line to this one marked by beta, right? So it tells so what this sentence tells us is that if alpha is assumed, then we will be able to derive beta, and we know that for sure because we actually have been able to derive beta through these steps here, right? And so even though we can't use any of these lines appearing before as immediate steps for arriving to that line here, that's stepped out of the assumption, we can still make use of what happened here in the form of a summary, in the form of a sentence saying, that's what happened, we assumed alpha and we were able to conclude beta from it. And so you can think of the line that follows immediately after we step out of the assumption. You can think of that line, and usually that line always will be as a kind of summarizing line describing to us what mathematics took place in the previous argument. So in some sense, this thing is a proof of its own. So it's like a proof inside a proof, okay? Because the original thing was a proof, right? And so this thing is like a mini proof inside a proof. And what we're stating here is basically what has been proved by that other proof that appeared just before it. Okay, so that's the basic overview of the general structure of proofs. And by the way, I should say that A implies beta is not going to be the only way of stepping out from assumptions. We will also have other logical constructs here that can be used as summary of what happened in this mini proof that appeared before it, but that's what we will discuss in further detail in the subsequent videos. Okay, so let's just summarize what we discussed so far. Just in very few words, a mathematical proof consists of lines. Each line represents some mathematical statement, and these lines are logically related to each other, and their logical relationship is given by the spacing that appears before the line. So every time we have a line with the very first line that has space in front of it compared to the previous line, that line is treated as an assumption. So this is something we don't have to confirm, we can just assume this is correct. And in this example, we also have a second line like that, as a second assumption. And then all the other lines that appear, that are aligned in the same way as the previous one is. These lines, like this one and this one, are conclusions from the lines that appeared before. And so these conclusions have been made, should be made by given logical rules. The same applies here. This is also a conclusion because it is aligned with that very first line there. And this one is a conclusion as well. So we've got assumptions and we've got conclusions. And just one thing that I've forgotten, which is kind of the thing that reflects the name for a proof structure like this, which, as I said before, or maybe I didn't say, is actually based on the existing proof structure in logic, although with this bracket proof structure we have some minor differences in terms of presentation. So that thing that I forgot is the placement of brackets. So in order to keep track of this spacing, it might be difficult in text to keep track of the spacing, a bit confusing. So to clarify that, we use brackets to indicate. So every time a new assumption is being introduced, there is a vertical bracket that will open up there. And just before stepping out of the assumption, the vertical bracket will close. And so in this case, there will be two vertical brackets. And if I want to also bracket the entire proof, I can do that as well by placing a bracket here and then there. But usually we don't do that because the first line was empty, so there were kind of no assumptions in the beginning. So the standard way is not to have a bracket there. That's the summary of the bracket notation for mathematical proofs. As I said, in the next videos we're going to see how this bracket notation works for specific types of mathematical statements which can be used either as assumptions or as conclusions.